Okay, let's dive right into this explainer where we are going to decode the invisible chemistry holding our modern world together. Today, we're focusing entirely on the highly engineered classifications of chemical and mineral admixtures. These are the unsung heroes that literally transform conventional concrete from a basic, everyday building block into a highly advanced supermaterial.
Here's our roadmap. We'll start with the magic of how admixtures actually work, look at the great divide between chemical and mineral categories, dive into setting rules and heavy lifters, touch on some special extras, and finally, look at how we're engineering the future.
Section 1. The Magic of Admixtures, Redefining Concrete.
It's time we stop thinking of concrete as just a boring, static gray block. Instead, I want you to think of it as a dynamic, highly customizable chemical recipe. An admixture is officially defined as an ingredient added to concrete before or during mixing to improve its workability, durability, and setting times. Just like a master baker adds a pinch of yeast to make bread rise or specific salts to completely change the texture, structural engineers add these incredibly specific chemical and mineral ingredients to make concrete do impossible things under immense stress.
Our primary goal here is modifying that base recipe for ultimate strength, long-term durability, and crucially, survival in extreme environments. Just a few tiny tweaks to this chemical recipe can completely change how our structures behave in the real world. We're talking about taking a basic mix and turning it into something capable of withstanding freezing Arctic temperatures or even intense oceanic salt exposure.
Section 2. The Great Divide, Chemical versus Mineral. So here's the crucial point. This massive, complex world of admixtures is split into two primary branches, and these dictate exactly how and when they react within the mix. Here's our main taxonomy. On one side, we have chemical admixtures. These are your water-soluble compounds, the fast-acting modifiers used mostly to control setting times, early hardening, and water reduction. On the other side, we have mineral admixtures. Now, these are fine, inorganic solids with pozzolanic properties. That basically means they react chemically with moisture to form a super strong, cement-like glue. They add real, physical mass and long-term durability to the structure.
When you look at the breakdown from the EB001 design manual, it is just fascinating how many highly engineered subcategories exist to achieve very specific effects. You've got accelerators like calcium chloride to speed up early strength, you have air-entraining agents that use salts of wood resins to improve freeze-thaw durability, there are even anti-washout admixtures utilizing cellulose for underwater placements. It really highlights that concrete design isn't just mixing mud, it's an exact, purpose-driven science.
Section 3. Chemical Admixtures, Setting Rules.
These soluble chemicals are all about speed, control, and workability. The main types we rely on are water-reducing agents, which are also known as plasticizers. Then we have air-entraining agents for that freeze-thaw protection we talked about, set-controlling chemicals to either speed up or slow down the curing process, and high-range superplasticizers. If you need your concrete to pour easily, but you absolutely cannot add structure-weakening water, well, this is your toolkit.
So how do these plasticizers actually work without compromising the strength of the concrete? Well, it's a four-step process. Step 1, you add the plasticizers to the mix. Step 2, these chemicals act directly as surface-active dispersing agents. Step 3, they actively reduce the surface tension of the water itself. And Step 4, because that surface tension is suddenly lower, the concrete's workability improves dramatically without having to add a single extra drop of water. You basically get a beautiful flowing mix that perfectly maintains its high structural integrity. It's brilliant.
And who exactly are the unseen heroes performing this surface tension magic? It's these complex-sounding chemical compounds, polycarboxylates and lignosulfonates. They are absolutely the chemical rock stars of water reduction, making sure that the concrete pours smoothly around incredibly dense steel rebar networks without turning into a weak, watery soup.
Section 4. Mineral admixtures, the heavy lifters. Okay, let's slow things down a bit and look at the heavy lifters of the concrete world. Here is their exact definition. Also called supplementary cementing materials, these are fine-grained inorganic materials that improve properties and make concrete more economical. Essentially what they're doing is physically replacing portions of standard Portland cement. This drastically enhances the long-term durability and structural mass of the build.
Here are the key players you need to know in the mineral category. Ground granulated blast furnace slag, Type F and Type C fly ash, silica fume, and metacolin. What's genuinely amazing here is that many of these materials, like the blast furnace slag and fly ash, are actually industrial byproducts from steel plants and coal power stations. By engineering them into our concrete, we're making our structures significantly more resourceful and environmentally friendly. We are literally turning industrial waste into structural gold.
Now, for those of you who love the technical chemistry details, notice how radically the chemical composition shifts when we compare ordinary Portland cement, or OPC, directly to these supplementary minerals. OPC is about 65% lime, right? But ground granulated blast furnace slag drops that to 40%, and silica fume has virtually zero lime. Meanwhile, the silica, alumina, and iron oxide percentages vary wildly. We are fundamentally altering the chemical DNA of the binder here to get exactly the performance we need.
Isolating just the silica content really reveals these extreme variations visually. Standard ordinary Portland cement sits at about 21% silica. Blast furnace slag pushes that up a bit to 35%. But look at silica fume. It brings a massive 90% silica content to the table. Because it's highly reactive and its particles are incredibly fine, introducing that much silica completely transforms the concrete's strength. It makes it incredibly dense and practically impermeable.
Section 5. Special and miscellaneous admixtures, the extras.
Of course, beyond the main chemical and mineral branches, sometimes our structural recipe calls for some highly specialized extras. The miscellaneous categories cover everything from bonding admixtures and corrosion inhibitors to shrinkage reducers, expansive admixtures, and even simple color pigments. From stopping rust dead in its tracks inside a bridge deck using corrosion inhibitors to simply changing the aesthetic color of a facade with pigments, these miscellaneous add-ins solve incredibly specific, real-world engineering challenges.
Section 6. Engineering the future, putting it together. Okay, let's bring all of this together. Why does this taxonomy actually matter for our future? Because by intelligently combining these classes of admixtures, we can engineer concrete for virtually any extreme environment on Earth. By blending the fast-acting chemical plasticizers to get the perfect flow, with the heavy-lifting mineral pozzolans for decades of durability, engineers can literally design a custom foundation for a skyscraper in a blistering desert or a massive bridge piling in the freezing Arctic Ocean. It's like a giant puzzle where we pick exactly the right pieces.
I'm going to leave you to ponder this final thought. As industrial byproducts continue to evolve and our world demands ever more sustainable construction practices, what will the next generation of highly engineered green concrete admixtures actually look like? What unexpected chemical or recycled mineral will we add to the recipe next to build the resilient cities of tomorrow? Thanks for joining me on this explainer, and keep questioning the science around you.